Bismillahir Rahmanir Rahim. Assalamu alaikum, my dear students. How are we today? Today, as you know, we will continue our discussion on the background to costs. As you know, we spent 2 lectures on developing the theory of production. We introduced the theory of the firm, we introduced the long run and short run, and concepts such as diminishing, marginal returns, and returns to scale, that is constant returns to scale, increasing returns to scale, decreasing returns to scale. Today, we will build on the concepts that we've learned, as well as develop some more ideas and concepts, especially graphically, that will help us understand how firms choose different combinations of inputs to produce a certain quantity of a good. Now, in our discussion of production and the theory of production, we defined the long run and short run respectively as situations in which the firm could change all the factors, that was the long run, and a situation in which the firm could not change at least one factor. Now, we introduced the law of diminishing marginal returns in the context of the short run. We looked at how a firm which used 2 factors, and when one of the factors was fixed, was receiving diminishing returns to increasing the quantity of the other factor or the variable factor in terms of the output of good produced or output of goods produced. We are working with only one good, as you know, so far, so we will continue to work with that. However, in the long run, we noted that the firm could make decisions such as the scale of operations, that is, whether it wanted to have one factory or 2 factories or 3 factories. So the scale of production was something that the firm was able to and had to decide on. The firm also had to decide on the location of the industry, of the firm, of the factories, where it wanted to set up the plant. And we noted the factors which determined the location decisions by firms. We also saw what external economies of scale and external diseconomies of scale were. And these were discussed in the context of how industry-wide developments affected any individual firm. And we gave the example of Pepsi advertising for its brand, but that also helping Coca-Cola, because any advertising campaign which increases the demand for Pepsi also might increase the demand for soft drinks in general and also might help Coca-Cola. So we discussed that dimension as well. Where we left the discussion in our previous lecture was when firms had to decide the optimum combination of inputs that had to be used in order to produce a certain quantity of output. So we discussed the marginal diminishing returns, the law of marginal diminishing returns, and how the ratio of marginal physical products to price had to be equated across those different factors in order to ensure that the minimum cost method of producing a particular quantity of output obtained. So we are in the realm of choosing the optimum combination of factors. We've introduced the marginal physical product approach. Today, we will talk about the isoquant or isocost approach. Now, in understanding what isoquants are, I'd like to refresh you of your understanding of indifference curves. Recall how any one indifference curve, which was downward sloping and was bowed in towards the origin, measured the different combinations or captured the different combinations of the 2 goods that the consumer was consuming in order to yield the same level of utility. So all the points along the indifference curve were consistent with the same level of utility for the consumer. Now, it is exactly the same principle that we extend to production. And what we basically draw now is what combinations of factors, not goods, but what combinations of factors can be used to produce the same level of output. So we will again have a downward sloping curve. We will call it an isoquant. Iso stands for the same. So iso means the same. Quant means quantity. So the isoquant will be a curve which captures all the different combinations of the factors of production that the firm is employing to produce a certain given level of output. To make matters simple, or to keep matters easy, we will work with two factors of production. We'll take capital and labor. We'll put capital on the vertical axis and labor on the horizontal axis. Let's use our graphical illustrations to see what isoquants are and what can we understand about production decisions or the decision about the optimum combination of inputs from them. Let's go to our first slide. Now imagine that our firm wants to produce a certain level of output, say 5,000 units of a particular good. Let us assume that it estimates all the possible combinations of labor and capital that could produce that level of output. Some of these estimates are shown in the table. Now as you can see, Technique A, I'll call it Technique A because it's a certain way of producing 5,000 units of that particular good. There are other techniques as well. So let me call it Technique A, and this is a capital intensive technique. When I say capital intensive, it means that the ratio of capital employed to the labor force or the workforce employed is very high. So if you divide 40 by 5, you'll get 8, which means that for every laborer who is working, there are 8 units of capital or 8 machines at play. So technique A is a capital intensive technique which uses 40 units of capital and 5 workers. Now as we move towards technique E, labor is substituted for capital. What does this mean? Labor is substituted for capital. It means that labor is put in place of capital. So machines, the number of machines is being reduced and they are being replaced by increasing number of workers. So the technique now becomes more labor intensive. As you can see, the ratio of capital to labor for technique E is 4/50, which is a very small fraction. Compare it with that of technique A, which was 8. Now these alternative techniques for producing a given level of output can be plotted on a graph. The points are joined to form an isoquant. The figure here shows the 5,000 unit isoquant corresponding to the table. Now the isoquant shows the whole range of alternative ways of producing a given output. So not only does it have point A, point B, point C, point D, point E on it, it also includes all the intermediate points or intermediate combinations of capital and labor which can be used to produce the same 5,000 units of the good. Now note that this is exactly like an indifference curve, and just as we could draw an indifference map from an individual indifference curve, we can also draw an isoquant map which contains a whole series of isoquants, each on top of the other. Note again that the isoquants cannot intersect, and we discussed the intuition of why indifference curves could not intersect, and the same intuition applies here. Now look at this graph which gives the isoquant map. The higher the output, the further to the right will the isoquant be. So isoquant I5 here, which is to the most northeast of all the isoquants, represents a higher level of output than I4. I4 in turn represents a higher level of output than I3, and so on. So just to recap there, an isoquant captures all the different combinations of capital and labor which can be used to produce the same, the iso level of the quantity of a particular good. Now, I want to make sure that you do not confuse the isoquant with some of the other graphs that we've been using. So note that there are three other types of graphs that you can potentially confuse the isoquant with. And let me enumerate them in order. First of all, there was the production possibilities curve, or the production possibilities frontier. But note that the axes there were expressed in terms of goods. So you had one good on the vertical axis and the other good on the horizontal axis. And remember that the PPF was bowed out. It was not bowed in like an indifference curve. Also, remember that the PPF intersected the two axes. So unlike the indifference curve or the isoquant, which becomes asymptotic to the axes, the PPF actually touched the two axes. Now, what was the PPF capturing? The PPF was capturing the concept of opportunity cost and increasing opportunity cost. Because we had two goods on the vertical and horizontal axes respectively, we could illustrate the opportunity cost of producing more of one good. That is, as we moved down the PPF, we were producing more of the good on the horizontal axis and less of the good on the vertical axis. And we could illustrate the concept of opportunity cost as the number of units of good Y, which was on the vertical axis, foregone or given up, divided by the number of each extra unit of X, which was the good on the vertical axis. That was the PPF. Then we studied the production function, which had the axes as follows. We had the total physical product on the vertical axis and the individual factor on the horizontal axis. So the individual factor could be capital or labor. Note now that we are in the realm of one good. There is only one good here, not two goods. And also we only have one factor, not two factors. We are drawing the graph in two dimensions. So on the vertical axis you have TPP, and on the horizontal axis you have labor or capital. And we saw that the TPP is a concave function. It goes up, then there is a turning point, and then it comes down. And this is what captures the law of diminishing marginal returns. Then the third graph that you can possibly confuse the isoquant with is that of indifference curves. But remember, the distinction is simple. Indifference curves are used in the analysis of consumption. Indifference curves relate to the same level of utility that a consumer derives from consuming different combinations of two goods, right? In an isoquant, we have two factors at play. So the axes are now not goods, but they are factors. You have labor on the horizontal axis and capital on the vertical axis. And the isoquant captures the different combinations of labor and capital that produce the same level of output. Okay? Now, once you are familiar with what an isoquant is and what the axes of an isoquant are, let's try to understand what determines the slope of the isoquant. Now, as you can see, there is this term MRTS appearing, and you must be wondering what the hell this is. MRTS mainly stands for marginal rate of technical substitution. You might recall that we introduced the concept of MRS, which was the marginal rate of substitution, in our discussion of utility analysis. And we saw that the marginal rate of substitution was the slope of the indifference curve at any point. And then we showed that it was also equal to the ratio of the marginal utility of the good appearing on the horizontal axis divided by the marginal utility of the good appearing on the vertical axis. So MRS was equal to delta Y over delta X is equal to MUX over MUY. That was utility analysis. In production analysis or firm's output decisions, MRTS is the exact analog of the MRS concept. The only things that change are that MU, marginal utility, is replaced by marginal physical product, right? And the total utility obviously is replaced by total output. Let's try to understand how the MRTS concept can be developed through our understanding of indifference curves, isoquants. I've gotten confused myself. And then see why this concept is useful in order for us to understand how a firm reaches or decides the optimum combination of inputs used in production. Let's go to our slide. Now, definitionally, the marginal rate of technical substitution is the amount of one factor, example capital, that can be replaced by a 1 unit increase in the other factor, let's say labor, if output is to be held constant. Therefore, if 2 units of capital could be replaced by 1 unit of labor, then the marginal rate of technical substitution would be equal to delta K over delta L is equal to 2 over 1 is equal to 2. But in a graph of which plots the isoquant and which uses the axes K and L on the vertical and horizontal axes respectively, the marginal rate of technical substitution is exactly equal to the slope of the isoquant. To be precise, the MRTS between 2 points on the isoquant will equal the slope of the line joining those 2 points. Thus, in the figure here, the MRTS between points G and H is 2. That is, delta K over delta L is equal to 2 over 1. But this is merely the slope of the line joining points G and H, ignoring the negative sign, of course. Now, crucially, the MRTS is also equal to the ratio of the marginal productivity or the marginal physical product of labor to the marginal physical product of capital. How is this? Now, as you can see, in moving from point G to H, the loss in output due to a reduction in the employment of capital is delta K times MPPK, where delta K would be 2 and MPPK would be MPPK. Whereas the gain in output due to the increased utilization of labor or the higher number of workers would be given by delta L, which is the change in the number of workers, multiplied by MPPL, which is the marginal physical product of each extra laborer. Now, rearranging, we can say that delta K over delta L is equal to MPPL over MPPK. But since delta K over delta L has already been established as the marginal rate of technical substitution, we can see how the MRTS equals the ratio of the marginal physical products of the 2 factors, labor and capital. Note that as in the case of the marginal rate of substitution, the 2 formula for the MRS, that is delta y over delta x equals to mu x over mu y, we have the same thing here, that the MRTS is equal to delta K over delta L, but the positions of L and K are reversed in the other formula, that is in the marginal physical product formula. There MPPL is on top and MPPK is in the denominator. Now, if you understand the marginal rate of technical substitution well, then you can also understand why the isoquant is downward sloping and why it is bowed in towards the origin, like the indifference curve. And the point here simply is that the MRTS is a ratio of the 2 marginal physical products. And now you have to see what is happening to the marginal physical products as you move from the northwest point on the isoquant to the southeast point of the isoquant. Now, as you move from the northwest point of the isoquant to the southeast point, you will notice that the quantity of labor being employed is increasing, whereas the quantity of capital is decreasing. Now, because of the law of diminishing marginal returns, as more and more of one factor is employed, the returns in terms of output to that factor fall. So the MPPL will fall as you move down the isoquant and employ more and more labor. On the other hand, the MPPK would rise as you are using less and less capital. This basically explains why the marginal rate of technical substitution falls as we move from the top to the bottom, that is, as we move along the indifference curve. Now, with that understanding of the marginal rate of technical substitution, let's see how an isoquant can help us illustrate returns to scale and returns to factor. Now, the second one, that is returns to factor, simply relates to the law of diminishing marginal returns, whereas the first one simply relates to, yes, increasing returns to scale, decreasing returns to scale, or constant returns to scale. Now, one question that should come to your minds is that one of these relates to or is a long-run concept. That is, the first one is a long-run concept where both the factors can be changed, both labor and capital, and if there are other factors, they can also be changed. Whereas the second one, which relates to the diminishing marginal returns law, is a short-run concept in which we assume that one of the factors is fixed, whereas the other one is being varied, and we study how the marginal physical product responds to the change in the quantity of that factor employed. Well, don't worry. We'll show exactly how the same isoquant analysis can help explain both a long-run concept and a short-run concept without violating any of the assumptions that I have told you to use intensively in your analysis of production. Let's go to our slides to see how the isoquant can illustrate these two concepts. So here we see how isoquants can illustrate constant, increasing, and decreasing returns to scale. Let's first look at figure 1. Now, in figure 1, you will see that the isoquant map contains isoquants which are equally spaced. That is, the distance between the 200 isoquant and 300 isoquant is the same as the distance between the 300 isoquant and the 400 isoquant. And note that when I am talking about distance, I am talking about the intersection points of a 45-degree line drawn from the origin towards the northeast, and the points that intersect with the isoquants of that line. So I'm talking about points A, point B, point C, and all the other points that intersect the isoquants. So if you notice, the distance between point A and the next point of intersection is the same as the distance between that point of intersection and point B. Now, these equally spaced isoquants capture the constant returns to scale feature of this production process. Now, if you go back to the definition of constant returns to scale, you will remember that constant returns to scale obtain when the percentage change in the output is exactly equal to the percentage increase in all the inputs. Now, let's see what's happening in this case. As you move from A to B, both labor and capital are being increased by, yes, 100%. Labor goes up to 2, so the increase is 2 minus 1 over 1, that is 100%. And capital is also being increased by 100%, that is 2 minus 1 over 1, right? So both the inputs are being increased by 100%. But as you can see, output also increases by 100%. That is, it goes to 400 from 200. And therefore 400 minus 200 over 200 is also equal to 100%. Note that the constant returns to scale feature persists in moving from B to C. Now when you move from B to C, both the inputs are now being increased by 50%. Yes, when you increase labor from 2 to 3, you get a 50% increase in the quantity of labor employed. Similarly, capital increases by 50%. Now let's look at what's happening to output. Output increases by 600 minus 400 over 400, and that gives you 1 over 2 or 50%. So the constant returns to scale feature is satisfied here. Now let's look at figure 2. Now here, the key distinguishing factor of this figure from the previous one is that the isoquants are becoming bunched together. That is, they are becoming closer and closer to each other. So the distance between A and the next intersection point of the 45-degree line R with the next isoquant is bigger than the distance between that intersection point and point B. So the isoquants are becoming closer and closer to each other. Now what is the implication of this? The implication of this is as follows. In moving from A to B, the constant returns to scale assumption seems to be satisfied because inputs increase by 100% and output also seems to be increasing by 100%. But note now what happens when we move from B to C. Here, inputs increase by 50%, but output goes up to 700, and the resultant percentage increase in output is 700 minus 400 over 400, which is 75%. And this is the case of increasing returns to scale, because the percentage increase in output exceeds or is greater than the percentage increase in both the inputs. Now let's look at figure 3. Here you can see that the isoquants are becoming further and further apart from each other. So the distance between any two adjacent points of intersection is increasing. So the distance between A and the next point of intersection is less than the distance between that point of intersection and point B, and then the distance between B and C is bigger than the previous corresponding distance. Now what is the implication of this? As you can see, in moving from A to B, constant returns to scale obtain. That is, 100% increase in inputs is matched by 100% increase in output from 200 to 400. However, from B to C, output increases only by 100, and therefore the percentage increase in output corresponding to a 50% increase in inputs is only 25%. That is 500 minus 400 over 400. Interesting, isn't it? Now let's look at how isoquants can help us illustrate the concept of returns to factor. Now, this is where some of you might get confused, in that returns to factor is a short-run concept, and how come isoquants, which essentially relate to a situation in which both capital and labor vary, can explain a short-run concept, which basically assumes that one of the factors is fixed. Now, the answer is very simple. Even using isoquants, we can assume that one of the factors is fixed. Let's see through a slide how this can obtain. Now, in the figure shown, it is assumed that capital is fixed in supply at a level of K bar. Output can only be increased by increasing the amount of the variable factor L. That is, we can only move horizontally from one isoquant to the other. We can't move in the 45-degree direction that we earlier assumed. Now we can only move to a higher isoquant by increasing
the number of laborers employed. So we move from isoquant I1 to I2 by increasing the number of laborers from L1 to L2. Note that a very small increase in the number of laborers is required to allow us to make the jump from I1 to I2. However, as we move further and further to the right, we need much larger increases in labor. That is, L3 minus L2 is bigger than L2 minus L1, although it is also giving us the same benefit. That is, we are also still jumping to 1 degree higher isoquant, not 2 or 3 degrees. Similarly, L4 minus L3 is bigger than L3 minus L2, and L5 minus L4 is bigger than L4 minus L3, and so on. Now, it is the curvature of the isoquants which gives us these diminishing marginal returns. Why are these diminishing marginal returns? Because initially a large output increase obtains due to a small increase in labor. But as we increase labor employed, we need much larger increases in labor to give us the same increase, incremental increase in output. So while L1 to L2 also gives us the same increase in output, L5 to L6, which is a much larger increase, also gives us the same increase in output. Now think of what would happen if the isoquants were not bowed in towards the origin. That is, if they were straight lines. If they were straight lines, you can see that the gaps would remain equal. And this illustrates how the diminishing marginal returns law is embedded in the bowed in shape of the isoquants. There would be no diminishing returns if the isoquants were straight lines as they are shown here. Now, so far we've assumed that the isoquants are equally spaced. Remember that the spacing of the isoquants relates to returns to scale. So far we've assumed that the returns to scale are constant. But what happens if we are in the realm of increasing returns to scale? That is, the distance between I1 and I2 is greater than the distance between I2 and I3, and this is greater than the distance between I3 and I4, and so on. Now, it is possible to have non-diminishing or non-falling returns to factor. That is, as we increase labor from L1 to L2, we make the jump from I1 to I2. However, because the isoquants are bunched together increasingly as we move to the right, we still get the same distance, horizontal distance, on the horizontal axis. That is, L3 minus L2 is the same as L2 minus L1, and L4 minus L3 is the same as L3 minus L2. This graph shows how, in the presence of increasing returns to scale, you can have non-diminishing returns to labor or any individual factor. Now we've seen there how the concept of isoquants can help us illustrate returns to scale and diminishing returns to factor, and how these two can together be combined in the analysis of isoquants. But what we haven't discussed so far is what is the optimal quantity of factors that the firms should employ. We've seen in the case of the marginal utility or the marginal physical product approach that the optimal combination of inputs is where the MPP over P of that factor, that is the MPP L over the wage rate, should be equal to the MPP K over the cost of renting capital. So where the ratio of the marginal physical products to the last dollar spent on those factors are equal. But we haven't quite done that in the case of isoquants, and we need to see how that is done. Now, in order to do that, we need to introduce the concept of
isocosts. Now remember that we introduced the budget line when we were discussing indifference curves. Here, the analogous concept of that is that of isocosts. And the isocost is merely the line, it is similar to the budget line. It is merely the line which captures all the different combinations of labor and capital, or whatever the two factors are, that the firm can afford to hire. You know, I mean, if the firm had an infinite budget or an unlimited budget, it would produce an infinite quantity of goods, right? By using an infinite quantity of labor and capital. There would be no bar on how high the isoquant could go. So in order to put a check on how high the firm can go, we need to put a constraint on the graph of the isoquant map. And that constraint comes in the form of isocosts. Let's illustrate this through the use of a slide. Assume here first that factor prices are fixed. That is, the price of labor and the price of capital are fixed. And assume also that the firm's budget is fixed. Let's say that the firm's budget is rupees 300,000. Now a table can be constructed showing the various combinations of factors that the firm can use for a particular budget, which in this case is rupees 300,000. For example, assuming that PK, that is the price of capital, is rupees 20,000 per unit and PL is rupees 10,000 per worker, the table here shows various combinations of capital and labor that would cost the firm rupees 300,000. These figures can then be plotted on the graph. The line joining the points is called an isocost. It shows all the combinations of labor and capital that cost rupees 300,000. As with isoquants, a series of isocosts can be drawn. Each one represents a particular cost to the firm. The higher the isocost, or the higher the cost, the further out to the right will the isocost be. This is very similar to how we drew different budget lines, assuming that different consumers could have different budgets, or the same consumer could have different budgets at different points in time. And here, simply we are replacing the budget with the cost budget that a particular firm has. That is, how much can a firm buy of labor and capital from the money that it has. Now, we answer two questions that we answered also in the context of budget lines. That is, what causes the budget line to shift inwards and outwards, and what causes its slope to change. And we'll answer the same two questions here in the context of isocosts. What will happen to the isocost if the prices of both labor and capital rise by the same percentage? This, my friends, will cause an inward shift. So if the price of labor and capital both rise by 33%, the isocost will shift inwards as shown here, where it intersects the vertical axis at 10 and the horizontal axis at 20. Now assume that the wage rate alone rises to rupees 15,000 and that nothing happens to the price of capital. What will happen to the isocost? In this particular case, the isocost will pivot in. As you can see, the intersection point on the horizontal axis will change from 30 to 20 because the firm can now hire less labor from the 300,000 that it has as its budget. Now, my friends, any guesses as to what the slope of the isocost line will be? You know that it is constant because it's a straight line, and a straight line has a constant slope. Now recall the discussion that we had in the context of the budget line and what its slope was in utility analysis. There we saw that the slope of the budget line was simply Px divided by Py, where x was the good appearing on the horizontal axis and y was the good on the vertical axis. The exact same analogy applies here as well. The slope of the isocost is PL over PK, where L is, yes, labor, which appears on the horizontal axis, and K is capital, which appears on the vertical axis. So the slope of the isocost line is the ratio of the price of labor to the price of capital. And in this particular case, that would be 10,000 divided by 20,000, which is equal to 1/2. Now, once we've understood what the slope of the isocost line is, we can now move to a combination of the analysis of the isocost and the isoquants. We can put the two on the same graph. And as we did in indifference curve analysis, we can see how, in this case, the optimum combination of labor and capital will obtain. Let's go to a graph to see how this happens. Now, by combining isocosts and isoquants, we can answer two questions. One, what is the least cost way of producing a particular level of output? And B, what is the highest output that can be achieved for a given cost of production? The figure that is shown here first gives the level of output, that is 5,000 unit. Let's start with the first question, that is finding the least cost combination of factors to produce a given level of output. Let's take the level of output as 5,000 units, and let's draw the isoquant for this 5,000 units in our KL space. Now, a series of isocosts are drawn representing different levels of total cost or total budget of the firm. The higher the level of total cost, the further out will be the isocost. The least cost combination of labor and capital is shown at the point of tangency between the isocost and the isoquant. This happens at point R, where TC, that is total cost, is equal to rupees 400,000. This is the point where the isoquant just touches the lowest possible isocost. Any other point on the isoquant, example S or T, would be on a higher isocost. Now note, my friends, that this approach, that is the isoquant approach, takes the optimum combination of capital and labor as that point on which the isocost is tangent to the isoquant. So the ratio of the prices of labor to capital is equal to the ratio of the marginal product or the marginal physical products of labor to capital. So in other words, the optimum combination occurs where PL over PK is equal to MPPL over MPPK. But this can be rearranged to yield MPPL over PL is equal to MPPK over PK, which is the equimarginal principle that we introduced earlier in our discussion of the short-run production theory. So you see that the isoquant approach gives you the exact same result as the marginal physical product approach. And this is consistent with how the indifference curve analysis gave us the same answer as the marginal utility analysis approach. Now we saw in the previous slide how the least cost combination of inputs had to be chosen when you were given a level of output. But the second question that we posed, and we said that the isoquant approach could help us answer, was how the maximum level of output can be obtained given any level of budget that the firm has. Let's look at a graph to see how this can happen. Now here, a series of isoquants, not isocosts, but a series of isoquants can be drawn, representing different levels of total output or total physical product. The higher the level of output, the further out will lie the corresponding isoquant. The point at which the isocost
touches the highest isoquant will give the factor combination yielding the highest output for that level of costs. This will be at point H in the figure. Again, this will be where the slopes of the isocost and the isoquant are the same. That is where PL over PK is equal to MPPL over MPPK is equal to the marginal rate of technical substitution. If the prices of factors change, new isocosts will have to be drawn. Thus, in the figure, if wages go up, less labor can be used for a given sum of money. The isocost will swing inwards around point X. Thus, the isocost will get steeper, and less labor will now be used relative to capital. That is, the ratio of labor to capital will fall. That is, we will be in the realm of a more capital-intensive project. Less labor will now be used relative to capital. That is, the ratio L over K will fall. That is, we will move to a more capital-intensive process from a more labor-intensive process. So, my friends, by answering that last question, that is, what is the optimum combination of inputs that a firm should use, we've answered the third question that a firm had to answer when it was operating in the long run. Remember that the first question was, what scale of operations should it choose, whether it should operate at a large scale or a small scale. The second question was, where should it produce, that is, what should it be, what should be its location. And the third question was, what should the optimum combination of inputs be for it to use to produce a certain level of goods. And we've answered all those three questions, one by using the marginal physical product approach, and also today by using the isoquant approach. With that, we've concluded the long run and short run theories of production. Now what I want to do is to get to the bottom of what are the long run and short run costs in economics. Now, as you know, economists view costs differently from accountants. And we discussed the different types of costs that economists thought of. They thought about opportunity costs. They thought about sunk costs. And they said that sunk costs should not be included in the rational person's decision-making process, whereas opportunity costs should be included. Now, let me illustrate these two concepts, that is, sunk costs and opportunity costs, in the context of firms, and how firms view these costs and confront them in their day-to-day decision-making process. Now, look at sunk costs first. Imagine a person who sells flowers. Let's say he assumes that the market demand for flowers is 50. That is, he will be able to sell 50 flowers on a particular day. So he buys 50 flowers at the cost of rupees 2 per flower. Now, when he actually goes out to sell the flowers in the market, he discovers that the demand is only 25 flowers. That is, he will be left with 25 flowers which he bought at rupees 2 per flower. However, he notices also that if he reduces his price to, let's say, rupees 2 or rupees 1.5, then he can sell some of those flowers. That is, he might be able to sell the entire stock of 50 because he's lowered his price. But if he still thought about the cost that he had incurred for the flowers, that is the rupees 2 per flower cost, he might hesitate to sell the flowers at rupees 2 or rupees 1.5, and he might still want to sell them at rupees 3. But this would be paying too much attention to sunk costs. The cost of rupees 2 per flower that he has incurred is a sunk cost. This should not affect his decision of what price to charge in the future. You know, flowers are perishable items. If you don't sell them, they are lost. So the optimal decision or the rational decision for this producer or the seller of flowers is to charge the lower price and get rid of the flowers
and in a way cut his losses to the highest possible extent. Now let's try to understand what opportunity costs mean to firms. Now here we need to make the distinction between implicit and explicit costs. Explicit costs are those that have to be paid for in cash. That is, you have to pay them from your pocket directly. So if a firm wants to hire more labor, that it wants to use more labor in its production process, it has to pay the laborers wages from its pocket. So they have to be paid in cash. However, this is not the case for implicit costs. And think here of a firm who owns a building or a piece of land on which the plant is built or whatever. Now, is there a cost that the firm incurs in using that building that it already owns? Well, there is no cash cost to think of directly. It doesn't have to pay anybody a certain amount of money in order to use that building. However, there is an opportunity cost of using that building. And the opportunity cost is the revenues or the rent that the firm could have received if it had put the building or leased the building to someone else. That is, if it had not used the building for making the plant and using it for production. It could have rented the building out to some other firm. So that is the opportunity cost of using the building that it already owns. This is a distinction between implicit and explicit costs that economists pay a lot of attention to. So, my friends, with that, we come to the end of today's lecture. In our next lecture, we will talk a little bit more about costs. And we'll talk first about short-run costs and then about long-run costs. Critically, we'll distinguish between variable costs and fixed costs, and total costs and average costs. We will also, as we always do, talk about marginal costs, and we look at the different relationships between these costs. So till the next lecture, go home, enjoy yourself, look at some of those questions I've put up for you on the web, and then come back in the next lecture refreshed for a new discussion on costs. So till then, it's Khuda Hafiz and Assalamu Alaikum.